Let's maybe wait 1 or 2 more minutes. See if there's more student coming. I don't know why. Yeah, it's getting. Maybe I should take attendance next class. Yeah, not a lot of people on Zoom either. Because I think it's because we have every video lecture recorded. So let's give them the excuse to skip the class and maybe just watch the video. But the recorded video is intended for the asynchronized because those are maybe like part-time student. I do know there are students, they are working, only taking this course as a part-time student. Daytime they have to work. They only can watch the video maybe during the nighttime. Yeah. But also maybe this is there's ICCV submission deadline this Saturday morning. You know, I think there's a couple of students maybe also working on their paper. Yeah. James, you don't have any paper, or you are working on?
We're doing a resubmission.
Okay.
A new paper. We should be finishing today.
Okay. 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 Good. Good luck with the submission. Yeah. Yeah.
Actually, a question from last lecture.
Yeah.
Are all self-supervised pretext tasks just the data recovery tasks?
No, it depends on what kind of pre-task you have defined. Yeah.
If like you use like the image rotation and try to predict the rotation.
Yeah, that's more like a classification, right? So it's not recovery. I mean, predict rotation. Yeah, I mean recovery is more like you do some in-painting, right? You reconstruct or mask auto image modeling is mask autoencoder is you construct the patch, right? So and also like super resolution, recover the color, grayscale component. Those are considered like a sort of reconstruction or recovery task. But like for the rotation puzzles, they are more like a classification. Yeah.
Even like in a general sense, if you rotate the image, then you try to predict the rotation.
Yeah. Yeah, in a general sense, it's like recover the original position, right? So yeah, in a broader sense, it's more like how you understand the context. Yeah. Okay. Okay, so yeah, anyway, let's get started. So for today's lecture, we're gonna also talk about self-supervised learning because we also have other technique I want to discuss. But just to have a very quick recap, right? So the self-supervised learning is a subset of unsupervised learning method. The reason is because we don't generate the human labeled data, right? So we don't have human generated label. Basically, we're using some sort of design mechanism, right, to generate these labels automatically, right? So doing the rotation, all these reconstruction, all these supervision is already being there, right? You don't have to create new labels for the task. So why do we care about self-supervised learning? Is because a lot of real-world applications, the labels are very expensive, right? So like autonomous driving, all these semantic segmentation. So labels are very expensive to create, but you do have a huge amount of data, unlabeled data, right? So we want to leverage these unlabeled data and learn from them. So the self-supervised learning task is trying to define certain pretext tasks, right? Using freely available supervision, right? Rotation, recovery, all these, mechanism. So you can train a huge amount of unlabeled data using this pretext task. Hopefully, this pretext task is able to help the neural network learn meaningful representation. Then the next step is, just take the pre-trained model, right? Then we can using that to fine-tune it on downstream task, right? So which is the same as supervised training, right? In the supervised training, like ImageNet, we have all the labels for the training data. We train the model, right? The CNN network in the supervised way. Then we can leverage these pre-trained model for a lot of the tasks, right? Medical image analysis, remote sensing applications. But the self-supervised learning is just replacing the supervised training with all these human labeled data. but just using some pretext task, right, in the self-supervised manner. So, and we talk about a couple of very interesting and very effective, self-supervised pretext tasks, right? These are solving the puzzles, right? So basically, you have all these different patches, and you can randomly shuffle them, right? You have a bunch of different permutations. Then you feed in a random permutation to the neural network and ask the network, right, to predict what is the correct order of all these patches. So you come up with the original maybe object or thing in the input. And also a very effective method is predict the rotation, right? So you can rotate original image in different angles, right? From 0, 90, 180 to 270. And you ask the network, right, what is the original position, right? Or what is the rotation angle this image has been manipulated? And so these are some of the very popular self-supervised learning technique. And at the end, right, once the model is trained in the self-learning manner, we have to evaluate, right? So in order to evaluate how good is the self-superlearned representation is, we are using these self-supervised pre-trained model as some sort of feature extractor, right? So the pre-trained model. Then you have maybe another downstream database, right? So you can using this pre-trained model, fixed these couple of conv layers, right, as a feature extractor. Then you can maybe only train a linear classifier, right? Linear classifier on the downstream data set and trying to do the evaluation, right? If the feature representation is very good, right? So if you only train a linear classifier, you should also get very good classification accuracy, right? So that's how a lot of these, self-supervised learning works perform this kind of standard evaluation, protocol. So this figure just give you a comparison, right? So how these different self-supervised learning technique performs. So we have these, so the network backbone is AlexNet, very simple CNN network, right? So we have these, place 205 is a downstream task, right? We are using that as an evaluation data set, and we do the linear classification. So basically, we're using these different kind of self-supervised pre-trained model using different techniques. We're using them as a feature extractor. We only train the linear classifier layer on this data set and trying to do the classification accuracy comparison. And so here, this is the random initialization, right? There's no surprise, which is very low accuracy because everything is random. And you have this ImageNet supervised, right? So you have these ImageNet pre-trained model, and you're using that as a feature extractor, meaning that you don't tune these pre-trained like conv layers. You're using that as a feature extractor, only train the linear classifier for the place 205 classification, right? So you have 38%. But if you're using place 205 supervised, right? So that means you train this model using this particular data set and do the linear classification. You have a higher accuracy. So this is also reasonable, right? Because you are using the same domain data for training and testing. And the green bars, basically, give you the accuracy of all these different self-supervised learning technique, the pre-trained model, right? So this is jigsaw puzzle, colorization, split brain, right? So we talk about doing the color and the grayscale prediction simultaneously, and the rotation prediction, and also the clustering, right? So using all these different technique, pre-train a model, and do the linear, classification on this place 205 data set. So some of the performance are quite close to like ImageNet supervised training, right? So this is only 38%, but for like rotation prediction, you also have like around 34%, right? Only like 4% gap. So which is quite good because you are not essentially using any ImageNet, labels. And there's some other papers, right, trying to maybe do some more fair comparison, right? So like maybe the implementation can be different. So, they also reported there's maybe slight changes in result, right? So this is like jigsaw implement result actually is better than, the original paper has been reported. And also colorization slightly a little better, as the original paper reported. But they are pretty much on the same level of accuracy. And we also talk about the more recent like contrast learning, right, which is more advanced technique. So the idea is that if you have an original image, right, so you can do data augmentation to generate different, like 2 copies, right, from the original data, right? So this is the dog image, right? You can generate these augmentations, and this is another image. You can generate some augmentations from the original image. And the idea is that, if the augmentation coming from the same image, and they should be very close to each other, right, semantically, right, because they are just maybe different, small changes, right? Maybe this is one part of the object, and this is the other part of the object, or maybe some color changing. So they wouldn't change the semantic, concept or meaning of their original input. So in the feature embedding space, right, you want to pull them together. But if the augmented images, right, or patches, they coming from different input, right? So usually they are different. So you want their feature embedding to be far away from each other, right? Trying to repel the feature representation, right? So you want to have a very small cosine similarity between these augmentation from different input samples. Okay, so that's the idea of this contrastive learning. So basically, if you write like a more detailed cases, right? So you have all these different input, right? Different images represent different maybe potential semantic classes, and you can generate augmentations for each images, right? So then these augmented images will go through the same network backbone, right? Can be CNN or vision transformer, get the features. Then you can basically compute the similarity between the feature embedding, right? So the green block indicating these augmentations are come from the same class, right? So you want to pull them very close to each other. But for this kind of red blocks, right? So if you look at the first row, this one, right? This is the cat image, but this is patches from a different class, right? This is maybe a monkey class. So you want them to be far away from each other, right? So indicating by this red color. So if we, again, do this kind of a comparison as the previous one, right? So this is, using some of the context understanding, right? The jigsaw color prediction. And we can see that these contrastive learning-based method, right, is able to achieve much better performance, right? So if you can look at the same CRR, MoCo is another one, another contrastive learning method. So they achieve very good result. But there's also something, caveats we have to pay attention to is, in some of the papers, they are using different neural network architecture. So in a sense, they not be like 100% or purely of, we can get strictly fair comparison, right? If they are using a slight different network, then like doing this comparison may not be very fair, right? So that's something, small details you can pay attention to. And also maybe for your own work, right? So in the future, you want to do very fair comparison, make sure you are using the same architecture as your network backbone. Otherwise, I think if you write paper or submit a paper like this, reviewer maybe complain, right? So you are not doing a very fair comparison. And so for this SimCR paper, they also find, right, if you scale up your neural network, right, so the performance can get stronger, okay? And we also talk about this masked image modeling, or the later work masked autoencoder, right? So basically, we're trying to reconstruct a large portion of the masked out patches, right? So you have this kind of encoder-decoder structure. Encoder only sees these visible patches, right? whatever the visible information, the encoder will try to extract those meaningful representations, and hopefully, based on that, the decoder is able to reconstruct, understand the semantic geometry, everything, trying to predict the missing patches. So in this way, the encoder is able to learn very well representation, right? So actually, during the the linear classification, we are only using the encoder part, okay, because this is what we are aiming for, right? If we have very strong encoder, based on these limited visible patches, you are able to learn very meaningful representation to help the prediction, then that's what we want, right? And also there's a comparison, right? So this mask autoencoder and compare with this MoCo, contrastive learning strategies, right? So this is like version 3. They have a different, improvement at the different versions. And also they are comparing, even with, supervised, right, trained from scratch, right? So these, they have found that self-supervised training even outperforms, right, training from scratch, right? And also allows this kind of strategy scale to large VIT models, right? So if we have very large models, then it's usually very data hungry, right? So in this case, self-supervised learning actually has a lot of benefit, is very beneficial, right? Because we can collect a lot of unlabeled data, right? Then using this self-supervised learning to learn very generalizable features, right? So generalizability is really important because that will help a lot of downstream tasks and generalize to a lot of different data distributions as compared to the training data. So that's one thing that's really good for self-supervised learning because you can collect a bunch of data, right, to represent a very diverse data distribution. Rather like ImageNet or maybe other curated data set, their distribution may be also very limited or confined. Okay. So at the end of the last lecture, we also kind of mentioned a little bit, right? So a lot of cases we can using video, right, as a very strong source for the self-supervised learning because we can look at multiple images or frames from the video, and one natural supervision signal is the time, right? Because when we create such videos, how the motions evolve over time, right? How different actions or motions evolve over time has been already encoded in the original data. So actually, we can using that to guide the learning process, right? So we can, leverage the temporal continuity and the motion consistency, action orders, right? All these rich information can be used as the supervision to learn some meaningful representation from the video data. So let's look at a couple of examples, right? So how people have been explore video data for self-supervised learning. Okay. So the first one is the space-time cubic puzzle. So this is very easy to understand. We've talked about jigsaw puzzle, right? And actually two types of them. One is just predict one patch and the center patch, right? So the relation and also the permutation of 9 patches, which is more complex. So you can basically directly apply this kind of idea to video data, right? So basically you can extend to one more dimension. Not just 2D, but into the third dimension space, which is time. So here, their idea is that from the original images, you can, kind of crop out a lot of cuboid, right? So which is spatial temporal, kind of clips, right? You can consider. And then within this kind of cuboid, right? Basically, you can shuffle the the frame order, right? So you can randomly shuffle the frame order. So the time order has been kind of disturbed, right? And you can also rearrange the spatial configuration, right? So here they are selecting like 4 different crops of the each of the frame, right? But you can randomly shuffle these positions spatially. And now the question is, you ask the network on trying to rearrange all these like spatial and the temporal shuffled these kind of cuboid, right? So in this case, their task is trying to predict what is the right order spatially, right? So this maybe has to be the first, right? Then this is on the right, and then this is maybe A, B, C, D, right? So they have a specific order to rearrange this spatially. And also you can also predict the temporal order, right? So how these frames should be rearranged so that these motions can be more continuous, right? So the action will happen in the correct order, right? So the original shuffled one, their motion could be, randomly happen, right? So like maybe this is like a long jump action, right? So I see this in the sand pool, right? This athlete maybe performs some running and jumping, right? But when you shuffle that order, this can be changed, right? So you want to predict what is the right order. So this is their defined goal or pre-text task. They want to learn using the video data. And we do have a lot of, a large-scale video database, or you can basically crawl a lot of videos from YouTube or maybe other, social media website, right? You get a lot of these videos, then you can essentially train the model in the self-supervised learning way using this space-time cubic puzzle. So this is some of the results they reported, right? So they are using, different backbones, right? You have AlexNet, ResNet, 3D ResNet, right? And the C3D is also a 3D convolutional neural network, right? Because when we dealing with videos, it's better we are using these kind of 3D convolutional operations to extract spatial and temporal information at the same time, right? And this is some of the results, right? So they, compare with, this is the random initialized. So their self-supervised learning database is they are collecting videos from Kinetics database. So that's another very large scale data set for action recognition. So they are using Kinetics videos as their pre-training video. So they pre-train the model on the Kinetics model, then they evaluate on two downstream database, right? UCF101, which is, we in the CRCV, Dr. Shah, his student collected, which is one of the most used benchmarks for action recognition. And we also have HMDB 51 data set, which is another benchmark used a lot for action recognition. So in their case, with these pre-trained model on Kinetics, then we can do this kind of linear classifier fine-tuning and perform the classification on these two data sets, right? So they perform the comparison with other different method. So although, again, this just have some caveat, there are using different, backbones, right? So this may necessarily give you a very fair idea, right? How much improvement is actually coming from their self-training approach. Rather, there's also some, maybe differences because of the network backbone. So a more strict comparison would be using the same network architecture, right? So, but they do using this D3D architecture. Maybe this one you can do a very fair comparison side by side. Okay. And next, technique is also using the video, right? So they are using. Like the idea is we can track these moving objects, okay? So basically, you can, using some tracking algorithm, or maybe just compute very simple like optical flow, right? So optical flow is able to capture those moving objects. So then they're, in this figure, they're using this bounding box, right? Indicating the tracked object throughout the entire video, right? So maybe you can track from the first frame the same object to the end, right? So you can provide a trajectory, how these objects are kind of moving across this entire video. This is another example, the video, right? So you can do in the visual tracking to track this specific object, right? These bounding box will indicating the spatial and the temporal location across the entire video. Okay. And I think their idea is really, interesting. So what they're trying to do here is that, they want to measure, okay, this is the first frame, the tracked object, right, in the first frame. And this may be the tracked object in the last frame of this video, okay? And they want to compute, the distance, right? You can feed this into a neural network you wish to learn in the self-supervised learning manner, and you can extract the features, and you can compute the feature distance between these tracked patch, right? And you can also, compute maybe the first tracked, object in the first frame, and also some of the patch or object that is coming from a totally different video. Okay, so if you look at it visually, right, this is coming maybe a totally different object, right, coming from a different video. And you can also compute their feature distance, right? And the question is, how do we measure, right? What is the objective we want to define so that we can, get some meaningful, representations? So I want you to think about this, right? So here, right, this D parenthesis here is basically compute the feature distance of these tracked objects forming the same video. And here on the right side, okay, they are trying to compute these two tracked objects, which are coming from the can be total different videos. So what is this sign should be? Greater, equal, or less than, right? Do you think about this? What this should be? Less than, right? Yeah, so the intuition is that because we are using tracking to tracking the same object in the same video, I mean, let's just look at this one particular example, right? So this person riding the bike, right? How he is riding the bike can be different, right? Maybe the posture, the background can have a little bit of change, but still the same person, right? So, and riding the same bike, there's a lot of feature similarity, right? Because they're corresponding to the same object in the scene. So their features should be very close to each other, right? Because this tracking algorithm is tracking the same object. But if you look at the tracked object from two very different videos, so most likely these two objects will be totally different, right? This is a person, this may be some animals, or maybe some like cars, or some other things, right? So, semantically they can be very different. So in this case, in their feature embedding, their distance should be, larger, right? So their distance very large than the left one. Okay, so that's, their, intuition, right? So you can define this as your training objective, right? So you want the cosine distance between these tracked one to be smaller than the cosine distance of these tracked object from two different videos. Okay, so you can define your optimization objective like this, then you can optimize that. Okay. And just to mention something, another, the self-supervised, which I think maybe bears some similarity is, so I was also involved in some project doing the crowd counting. The crowd counting, which means you want to count how many person in one specific scene, right? Usually you have thousands, right? You have some parade or some meeting room, conference room. There's going to be hundreds of thousands of people, right? So you can imagine doing the annotation, like bounding box or even the dots, right? Heat map for each of the person, right? So it's going to be a very tedious, process if you want to do this in a fully supervised way. So there's also a lot of, application using self-supervised learning for crowd counting, right? So one idea I found is really interesting is what they have what they do is you have this crowd, images, right? So I'm just using bunch of dots to indicating, so many people in this crowd, okay? So in their one paper, what they do in the self-supervised learning way is they crop a patch, which can be like 50 by 50. Let's say this original image is 512. Okay. 512 by 512. Okay, so this is maybe like a 50 by 50 patch. Okay, so what they do also is, maybe based on the same center, right? You can crop a larger image, which maybe can be 100 by 100 or 200 by 200. Okay, then the objective is that the count, right, within the larger patch should be greater or equal to the small patch, right? So this is also something inherent, based on the nature of the data, right? So you have a crowd images, right? If you're a larger patch, then there's a high chance you have more people in the scene, right? So that's how they define. But yeah, this is not exactly like the video, but kind of similar idea, right? Based on the data, right? So here we are considering this is a tracked patch, right? Their feature similarity should be closer rather than two patches coming from totally different, video. Okay. So some other works also leveraging these videos is, based on the supervision of time, right? So basically we can learn from temporal ordering. Okay. So in this paper, they are selecting maybe 3 or 5 consecutive frames. Or you don't have to necessarily sample like consecutive frames. Maybe consecutive frame maybe don't have too much motion changes, right? You can sample maybe a certain interval to generate to have like 3 frames, but in their original order, okay? And then what you can do is you can change or shuffle their order, right? So randomly. And then in this case, you can create like so-called a positive tuple, right? So which means you have 3 frames that is in their original order or the correct order. And you can also create the negative tuples, right? Which means these 3 frames are not in the right order, right? Because we can shuffle them, okay? And what you can do is that you can feed these, positive tuple and a negative tuples into the network and trying to predict, right, the temporal order, or just to predict if this is the right order or this is the wrong order. Okay, so in this case, they are predicting if this is the right one or this is the negative one. Okay, so that's why they call this tuple verification, right? Is it correct or this is incorrect time order? Okay. So they also did this kind of evaluation, UCF101, right? So you can train this on a different database as the pre-training. Then you can do the linear classification on some downstream database, right? UCF101, HMDB51, and this give significant, boost as compared to just do the random initialization. Okay, so these are some of the cases you can use or leverage, right, the video data, right? So some of the, temporal consistency, motion orders, right? So to guide or supervise the learning process based on the video data. And based on these video data, we can also considering multimodalities, right? We can do this kind of cross-modality supervision, right? Because in some applications, maybe, collecting multimodal data is very simple or straightforward, right? Let's say you have certain sensors that inherently has multiple modalities, right? You have a LiDAR, you have a GPS or IMU, right? So you could compute this acceleration, and angle rotation, and maybe you also have cameras, right? So this is actually used a lot in self-driving applications, right? So although some companies they only using vision, but others can using multiple modalities, right? LiDAR, IMUs, camera together combined, right? So you are naturally collecting these synchronized multimodal data, right? So in this case, you can do this kind of cross-modality matching or prediction, okay? And if we only have like a single, camera modality, but some cases we do have RGB, right, which is the color image, but we also have depth, right? So the depth image, like time of flight, these cameras are also very common, right? So a lot of RGB depth camera are out there and are very cost effective. So you can simultaneously collect RGB images and also depth images, right? So depth corresponding the distance between the object and the camera, okay? So in this case, you can do this kind of RGB and the depth correspondence, right? So how you have like a paired, images, one RGB and the corresponding depth map. Then you can do this kind of cross modality learning, okay? And we can have image and text, right? So this is also very common, right? Especially, with these multimodal foundation model, right? So we have a lot of vision language models that based on images, videos, and the text, okay? And essentially, these are not, it's very easy to collect, right? So a lot of social media, users, they upload images, they have some, text, a hashtag, text descriptions, or you can using some, AI models to generate the text from the images, right? So then you can form image and text pair, and you can perform this kind of cross modality learning. So we'll talk about these examples. Video and audio is also kind of inherently, right? So when you do the collecting the videos, right, the audio is, most of the time you will have audio. Although some like surveillance cameras, they may not have audio, only have the videos, but any of the commercial, like the cell phones, you take a video, dash cameras, right? They will come videos and audios, right? So, and also as a human, right, when we do some recognition or reasoning, right, maybe recognize some certain actions, audios are also very important, right? Sometimes we look at both video and audio, right? So let's say, like a baby crying, right? So we don't even need to look at the video, the appearance, by listening to the audio, we can recognize what kind of action that is, right? So that has very high correlation, right, semantically, right, based on the appearance and also the audio information. So let's look at one example, that is we can using the audio and the visual correspondence, right? So here we have this video naturally has the synchronized appearance and also the audio information, and we can build these kind of correspondence, right? So first is we can take maybe the RGB videos from one videos, right? So we can feed these frames or maybe one images or a short clip into the vision network, right? So we can encode some visual information. And on the other hand, right, so we can also input an audio track, right? So this audio track may come from the same original video, or this audio track can be extracted from a totally different video, right? Then we feed this audio track into another network, right? Could be a different neural network architecture, or could be the same. And you can later fuse their features and trying to predict, right, if these two are corresponding to the same source, right? So if they actually coming from the same video, or these color information and the audio track are coming from two different videos, right? So you can do this kind of verification. So this is what they do, right? So they have these, they are using the same network architecture, they share the weights, right? So you have this visual feature and go through this VGG network, right? So you also have this audio track. Usually you can, doing some transformations, right? So using this kind of, MFCC, which is very common, when you're doing the audio or speech recognition, right? So it's like male frequency analysis, and you get this kind of spectrogram, so it's like image, right? Not like the natural image, but look like an image. And if you form that into an image, then you can, using the same, right, seeing architecture, then extract the features, then later do the fusion, then make the prediction, right? If it's a correspondence to each other or not, okay? So very simple, right? So you can using these two different modalities to do this learning, okay? Another example, which is very common, is using image and a text, right? So here I'm gonna using a clip model as a case study, okay? So this is widely used vision language model that you can using that for feature extractor for the images, and you can also using its text encoder to text embeddings from any input text. Okay, so basically CLIP stands for contrastive language and image pre-training. So it's a large-scale pre-trained model, right? So in the self-supervised learning manner, for designed for natural language processing and also vision task, right? Because it has image encoder and a text encoder. Once it's trained, then you can apply these encoders to whatever the task, right? Language or vision task you want. Okay. And by the name, right, contrastive language image pre-training, you can imagine they are using contrast learning technique, which we've already discussed. Okay, so this figure just give you some idea, right? So how the model is trained, right? So first of all, you can prepare, a lot of data, right? So actually they collect a huge data set, right? So you can crawl a lot of data from internet or maybe extract data from some existing large-scale database, right? So then you can prepare the text for the image, and you can have a text encoder, right, to extract the features from the text, right? So this like if this is a positive pair, which means the text is correspond to the image, and this is considered a text prompt, right? So you generate all these text embeddings, and similarly, right? So for all these different images, you can feed that into an image encoder to generate, this image feature embeddings, right? So you have n samples in this batch, right? So you have these different feature embeddings, right? From T1 to Tn. Here, from I1 to In, right? So I indicating image and T indicating text, okay? So for the diagonal part, which is, we know that this is a pair, right, based on their subscript, right? So these index indicating if they are coming from the same image and text pair, right? So if they are coming from the same and text pair, we want their features to be close to each other, okay? But the off diagonal, right, because we know they are coming from different images, so their feature embedding should be far away from each other, okay? So you can using this kind of contrast learning as the objective to learn from a huge amount of image and text pairs. Okay, so once you train in this way, right, so then one really good thing about this CLIP model is you can actually using it for zero-shot prediction, okay? Zero-shot means, you can predict image that maybe has never been trained or the concept has never been exposed during the training process, right? Let's say, a zebra, right, or maybe a type of dog, images has never been exposed during the training, but this model has the capability to do prediction or new or unknown classes, okay? So let me explain why the CLIP is able to achieve that, right? So as you can see that, right, in their testing, right, so they are giving a fixed prompt type or format or template, right? So this is a photo of something, right? A photo of object, right? So this object is the model has to predict, right? So what classes this object is, or bird, cat, car, etc. So because, when during the training, right, we are essentially call a lot of, data from the internet, and, these model has been exposed basically a lot of these kind of English text, right? So let me just using this kind of zebra as an example, right? So if during the training we've only seen horse, right, never exposed to examples like zebra, then how the model is able to predict that? So basically, if you feed a zebra image, right, and to this image encoder, and you may get some feature representations like a horse feature representation, right, because like the shape could be really similar to a horse, right, the standard horse. But you may also generate some features like black and white stripes, right, description, right, because that's a very distinctive feature from zebra. And what you can do is you're trying to find, right, for all these available text encoding, right? Because we can basically, feeding all these, dictionary, right, to this text encoder to generate some feature embedding, right? And we try to find which one is close to this feature, right? So for this image feature, maybe we find something like we have a horse shape, right, and also black and white stripe that's corresponding to this kind of text of a zebra, right? So in this case, right, we can do this kind of zero-shot prediction. So after the clip has been, widely used, right, and serving as a very strong encoder, either for text or image, there's a lot of work has been dedicated, right, to train better or using better strategies or maybe have more diverse data to train this, right, have better image and the text alignment, right, because how we can align these text embedding with the feature image visual embedding is also very important, right, so that the model is able to learn those strong alignment, they corresponding to the semantic concept. So a lot of research has been devoted to the feature alignment and come up with some very even stronger model as CLIP. So this one shows like how many like a vision language model has been worked on, and right now it's still there's a lot of model has been proposed for different tasks, right? Not just for classification, but for high-level reasoning, right? Generating text to visual question answering or grounding. So if you're interested, you can check this reference, and there's a lot of latest work published in these like a survey, right? Vision language models for vision task. Okay, so we've talked about all these different strategies, right, for self-supervised learning, right? So from the simple like rotation prediction to more complex, right? You can using videos or using cross-modality data. Now we want to see, right, so how some of the techniques can also be used in medical image computing. And this is really useful is because for medical images, right, getting these labels will be also, a very expensive task, right? So we have to ask the expert, right, doctors or physicians, right, to spend hours to label these data. But these doctors or physicians can be very busy sometimes, right? So and not all the general expert is able to generate these correct label. Because a lot of these domain knowledge require these experts trained years in order to have very correct label information. So that's why in the self-supervised learning manner is going to be really helpful in the medical domain, right? We don't rely on a huge amount of label data. So let's just look at this one particular papers. They are using self-supervised models for medical image classification. So what they do is they want to, again, using this self-supervised learning technique, but how we are able to, train better for the medical domain data, right? Because medical domain data can have a very large gap as compared to the natural images, right? So we have like X-ray, CT, MRI scans, right? Or maybe this kind of different applications, right? Skin, dermatology images, right, and also these lung or maybe brain images for diagnosis. So what they do is they come up, these kind of continuous, pre-training strategy. So what they have is they first using a super learning model that is trained on unlabeled natural images, right? And next is they further fine-tune or continuing the pre-training process on medical data, right? So you can collect all these medical data, right, without any labels, but you can use in the same strategy, right, to like contrastive learning or rotation prediction or whatever. You can continue, pre-train this model on the medical data, trying to reduce the domain gap, right? Because you directly apply to the medical data, the domain gap can be large, then the model may not be able to generalize well. But if you do this kind of domain-specific pre-training, hopefully that gap can be reduced. Once the medical domain pre-training is completed, then you can do a small like supervised fine-tuning, right? Have a very small amount of label data to do the fine-tuning, okay? So they are, again, so if you look at this one figure, right, they are using these contrastful learning technique, right? So for this chest X-ray, you are using augmentations, right? Using rotation, cropping, or maybe some other contrast changes to generate these two copies, right? Trying to maximize their agreement because they are coming from the same sample. And if you have using a different sample, you can do this generate negatives, pair. But in this case, we have this same SIAMS network, which only require a positive sample. You can do this contrast learning. And another strategy they explore is rather generate augmentations. You can also using some of the multi-view data or multi-instant data coming from some of the data set. Okay, so one example they show is for this dermatology images, right? For the same subject, they may take the same disease area multiple times, right, taken from different angles. So inherently, that can be like a positive images, right? You don't have to do any augmentation because in their data set, they have multi-view images, right? The same skin disease, same subject, but it's just, the camera taking from different angles. Then these multi-view images can be naturally considered as a type of augmentation. And semantically, they're corresponding to the same class, right? You can construct the positive pairs using, multiple such instances, right, from the data set. So that's what they call multi-instance contrastful learning, okay? So they do some experiment, right? So, technical-wise, there's nothing new, right? So it's again using this contrastful learning technique, but it's just how they, pre-train their model and how they construct the positive pairs has a little bit of difference as compared to the original, like same clear paper, okay? So here's what they find, right? So if you're using ImageNet pre-train, right? So this is the accuracy they can achieve. But if you're using ImageNet SimClear, right? Using self-supervised ImageNet pre-train, then you do the further pre-training, right? Doing the dermatologist data, then you can get some better improvement, okay? And this is similar for another chest X-ray, right, chest-spurt data set, and they are also able to get a little bit better, performance. Although the performance improvement is not that high, right? So for this particular data set, if you're just doing the chest expert pre-training, only gain like a 0.2 percentage. Okay, so just in summary, right? So we we have talked about different types of pre-test tasks, right? So it can be generative, right? So predicting part of the signals, right? So you can doing this kind of autoencoder, right? Doing masking the patches and doing the reconstruction. Or you can using this kind of autoregressive, which is used a lot in large language model, right? So you have a sentence, you're trying to predict the next token or next word, right? So this is again, this is like a generative, way to do this kind of self-supervised learning, right? You also have some discriminative, right? So predict something about the input signal, right? So the rotation angle, the clustering, auto contrastive, right? So or verification, right? If they same corresponding to the same video, corresponding to the same object, something like that, okay? And also you can using multi-modalities, right? Using some additional signal in addition to images, right? So you can use in video, 3D models, right? So if you have some 3D rendering of object or maybe 3D information, right? Like the depth image, right? So you can do this kind of cross-model matching, okay? And the audio, right? The sound. And the language is also very text, right, are very common. So we just talk about these two techniques. So nowadays for these, multimodal learning, usually, whatever the modality you can think about or you are able to collect data from, it's encouraged to using all these different modalities because they may have complementary information with each other, and you are able to learn very generalizable representations that you can adapt to different modalities, right, for the downstream task. Okay. Okay, all right, so here are some of the references, right? So if you're interested, I list a lot of surveys and also, also some of the self-super learning specifically, for medical image analysis, right? A deep dive into SSL for MIA, data models and tasks. So this is something, if you are interested in explore more for the medical application, you can read this, survey paper. Okay. Okay, all right, so I think that's all for today. And so if any questions, let me know, and we'll see you guys next week, okay? Any questions? Okay, great. I'll see you next week.